This is day 1 of Calculus BC, and in our first unit we talk about limits, continuity, and there are a couple of theorems that go along with continuity, and we get into derivatives. And we'll talk about the definition of derivative, and we'll talk about the basic rules of derivatives. So in these notes, we're talking about limits. So this is Unit 1 and Notes 1. And this is our section on limits. Okay, so first of all, we're going to talk about what is a limit. So a limit is a very complicated concept, but it's not difficult at all to use and to evaluate a limit. In general, limits are not a difficult thing, so you should not be afraid of limits at all. A general kind of working definition of a limit is just that a limit is the intended height of a function. It's the intended height. It's what the function's it's what the function wants its height to be. And that might sound a little confusing. We've dealt with a lot of functions in our time. We've dealt with some cubic functions, maybe something looks like that. We've dealt with some parabolas. We've dealt with some lines. These are all different functions. And the height of a function is just its y value. So the height is very simply, it's the function's y value. So a limit is the intended y value or height of a function. Okay, as we go from left to right, as x goes from left to right, the height changes, right? The y value changes for as we change x values, the y values change. So the height changes. So let's just, I'm going to take this little parabola, I'm going to make this be our very basic y is equal to x squared parabola. And let's take the point where x is 2. Well, when x is 2, what does the function want its height to be? Well, when x is 2, the height is up here. We can put 2 in for x. The height is going to be 4. So the height, the y value, is 4. So this point would be 2, 4. And so therefore, when I approach x, when x approaches 2, from either the left or the right, y approaches 4. Okay, so I can say there that the limit as x approaches 2 of our function x squared, that is equal to 4. And you might be saying, what the heck? Why am I doing all of this? Well, this is not a great representation of the power of a limit. This is just a function. This is just a function without any bells or whistle. It's just a kind of a basic little parabola. What gets more interesting is when we have other things going on with our functions. So yes, these are functions, and we've dealt with lots of functions. We've dealt with exponential functions, logarithmic functions. We've dealt with a lot of functions over our time. And some of the more interesting functions are ones where there's something additional going on. Like, what about, let's see, what if I take this function? Let's say I'm going to call f of x is equal to, let's say, x cubed minus 2x squared over, and there goes my pen. I'm going to grab a black pen here, over x minus 2. Let's take this function. And before I get too far into what we're doing with limits, let's just do a very quick little review. When you see a function like this, I see that the numerator can be factored, and I can take out an x squared, and if I take out an x squared, I'm left with x squared times x minus 2 in the numerator, and I still have that x minus 2 in the denominator. And we know something about this. We know that this x minus 2 and the x minus 2 on top and bottom, they can cancel each other out, right? However, if you cancel each other out and you get x squared, is x squared the same as what we started with? The answer is no, it's not. X squared is not the same as what we started with, because once we cancel these out, we've lost something. We've lost what happens in our function when x is equal to 2. Well, when x is equal to 2, this denominator is 0. And we can't have a denominator of 0. So, yes, these two are equal if x is not equal to 2. What happens on the graph when x is equal to 2? Well, when x is equal to 2, we have a hole. So this function is equal to x squared, except at x is equal to 2, and at that point you have a hole. So I could sketch this little graph, a little rough sketch, and that would be the graph of x squared, but now we know that at x is equal to 2, up here at this point, we have a hole. So there shouldn't be a little line through there. But anyway, I'm not going to get out my whiteout for that. Okay, so there's a hole there. So my question then, this becomes a more interesting example. So my question is, now what is the limit as x approaches 2 of this function? And I could rewrite this, or I could just say f of x. Writing f of x is a little bit briefer, so that's what I'm going to do. So what is this limit now? Okay, so remember what I said at the very beginning. A limit is the intended height of a function. A limit is what the function wants to go to, even if it doesn't go to. Okay, so what is the y value, what is the height that this function wants to be as x goes to 2? Well, as x goes to 2 from the left, as x goes to 2 from the left, this function does indeed go to 4. Let me go ahead and put this over here. From the left, this function goes to 4. And you know what? We have a way to write that using a limit. The limit as x approaches 2 from the left, the notation for from the left is we put a little negative sign up here. It looks like an exponent. It's not an exponent. It's just a superscript. And it's the notation for x approaching 2 from the left. Okay, of our function. And that limit from the left is equal to 4, because the y value as x approaches 2 from the left, let's say we put 1.9999999 in for x, what would that be? Well, that would be very, very, very close to 4. It would be 3.999999999, so very, very close to 4. The intended height is 4. Okay? Now let's approach 2 from the right. Let's come at 2 from the right. So if we're coming at 2 from the right, what is that intended y value? So the y value, as we approach, x approaches 2 from the right, the y value is still going to 4, right? So I could write that as a limit of the limit as x approaches 2 from the right. Our notation for from the right is this little plus superscript. That means that x is approaching 2 from the right. So that would be like 2.00000000001. All right, as we approach 2 from the right of our function, we find that that is also 4. If you put this value in for x, you get something slightly bigger than 4. Okay. If the limit from the right is equal to the limit from the left, if the limit from the left is equal to the limit from the right, then our limit is equal to that value. Okay, this is my little symbol for therefore, or so. All right. So this is a little bit more of an interesting concept now. So we don't care. A limit does not have to exist at the actual x value. Or, I'm sorry, the function does not have to exist at the actual x value for the limit to exist. Okay? If you have a hole, you're going to have a limit. Okay? Let's take a look at something else. Let's take a look at what if we had another kind of interesting function that you have seen in the past. Let's say that we have a little piecewise function. Okay, a little piecewise function. Let's keep our x squared. I'm kind of liking that. And let's say that f of x is equal to x squared if x is less than 2. Okay. And then let's make this maybe 7 minus x if x is greater than or equal to 2. So what would that graph look like? Let's see. We would have this a parabola for x less than 2. So when x is less than 2, we would have this parabola. And then it's not equal to, so I might have a little hole there. We'll see. All right, for 7 minus x, that would be a line with slope -1, y-intercept 7, and I know that this value here is 4, right? So 5, 6, 7. So this line would go through this, but we only want to draw it for x is greater than or equal to 2. So slope -1 would come down here. I would be starting up here at 5, and then my slope would continue at a -1 slope. So this function looks like that. So now my question is, what is the limit as x approaches 2 of the function now? Okay. Well, using the same approach that we used on the last problem, let's first examine the limit as x approaches 2 from the left, and then we'll examine the limit as x approaches 2 from the right, and if they are the same, then that's our limit. So from the left, as x approaches 2 from the left, our y value is approaching 4. So the y value would be 4 there. But from the right, approaching 2 from the right, our function value is approaching 5. Right? So these two values this time are not equal to each other. Therefore, this limit, the limit as x approaches 2, does not exist. Does not exist. We abbreviate that DNE, does not exist. Okay? So let's see what we found graphically. Graphically, what we found here. We found if you have a hole in the graph, then the limit exists and is equal to the y value of the whole. But if there's a break in the graph, like here there was a complete break in the graph, if there's a break in the graph, not including a hole as a break, if there's a break, then the limit does not exist at that x value. Yeah, so up here, the limit existed, like if I was finding the limit as x approaches -1, that limit exists, right? Because there's nothing funky or silly going on there at x equals -1. So the limit of this function exists lots of places, just not at x equals 2, as x is going to 2. Okay? All right, so graphically, we're off to a great start. Just a couple more things I need to talk about, talking about limits graphically, okay? And that involves what happens, we know that some graphs have asymptotes. So what happens when a graph has an asymptote? Let's think about that. Let's take a look at this function. Let's consider this. F of x is equal to x minus 1 over 2x minus 4. Okay? And I could graph this. If I were to graph that, what would that graph look like? Okay. What would that graph look like? Well, I see here that I can factor slightly this denominator, right? I could take a 2 out. In this case, this x minus 2 on the bottom, there is no factor of an x minus 2 in the numerator. So we're not going to have a hole anywhere, but we are going to have a vertical asymptote. We're going to have a vertical asymptote at x equals 2. So at x equals 2, we have this vertical asymptote. I'm going to draw a different color for that. Okay. All right. That's not part of the graph. It's just we know that that's going to happen here. Okay. And what about, since this is a rational function, it may have a horizontal asymptote, because some rational functions have a horizontal asymptote. Well, the horizontal asymptote is actually a limit. And you have found horizontal asymptotes before, but I would like you to start thinking of a horizontal asymptote as a limit. And a horizontal asymptote, let me write this down. A horizontal asymptote is a limit as x approaches infinity of the function, or as x approaches negative infinity of that function. Okay? You've never thought of it that way before, I realize that, but that's exactly what it is. This is a limit at infinity. Okay? We're asking ourselves, what does y get closer and closer to as x increases without bound? So x is going to infinity. It will never reach it, right? But we can increase x without bound, and we're asking ourselves, what is that y value? Isn't that what a horizontal asymptote is? Yes, it is. So we're actually finding the limit here as x approaches infinity, or negative infinity. And I'm going to go ahead and write the function in here this time. Okay, let's analyze this. If we sort of plug in an unbounded value for x, so think of the biggest number you can possibly think of and plug that number in for x. Here's what I'd like you to start to do. This minus 1 on top, if you have the biggest number that you can possibly think of, and you plug it in for x, and then you take 1 away from it, is this minus 1 going to have any effect on your large number? No, it is negligible. This minus 1 is negligible. Same with the minus 4. In fact, when you have a rational function like this, you only need to consider the highest degreed term on top and the highest degreed term on the bottom. Everything else is negligible. I should say this, if you have a polynomial over a polynomial, we can do that. Okay, so this is equal to the limit as x goes to infinity of x over 2x, because we can totally disregard the minus 1 on top and the minus 4 on the bottom. You can only do this if x is approaching infinity, all right? If x was approaching 5, you can't do that. These would not be equal, right? It only works for increasing to infinity or negative infinity. You can do it on both, okay? All right, now, since we are in a limit, we can reduce these x's. And when we reduce those x's, we get 1 over 2. And all of a sudden, we have lost our x's, and there's nothing to plug in x anywhere for, so this limit is just 1/2. Okay? You may have in your past math life found a horizontal asymptote by using a little rhyme. I think it is top, no, bottom, O, same, co. I don't care for that so much because I would like for you to think of it as this limit process. If you think of it as the limit process and how these are negligible, reduce your x's and then plug in the x for what remains, you're going to get the response to that same co whatever. You're going to find that the logical way rather than with a rhyme where you have no idea where it came from. Okay? The rhyme was for before you were aware of this limit process. Now that you're aware of it, I expect you to use it. Okay? And it'll help you later with what we're going to be doing next semester. So go ahead and do that now. By the way, if we had a negative infinity here, it would not have made a difference in this limit. We still would have gotten 1/2. So the horizontal asymptote is 1/2. Horizontal asymptote is 1/2. So if I were going to draw the horizontal asymptote, I would probably go ahead and draw it at 1/2. Okay. So we could plug in some values here to see exactly where this graph is, but let's just plug in. If we plug in 3 for x, we'll get 2 over 2, which is 1, right? So I know that this leg of the graph is up here. I'm just going to sketch it. This leg of the graph is up here. If I plug in, let's plug in 0 for x. If we plug in 0 for x, we get 1/4, so which is less than 1/2. So this leg is going to be looking something like that. Oops, got a little bit close to that. Oh, anyway, something like that. Okay. So now that we have that, we've already kind of naturally found the meaning of x going to infinity or x going to negative infinity. X going to infinity or negative infinity will give you a horizontal asymptote if it exists. It doesn't always, not everything has a horizontal asymptote, but if if this limit, if either of these limits is a number, not infinity, then you have a horizontal asymptote there. Okay? So now what do we do with this? What is the limit as x approaches 2 here? What's the limit as x approaches 2 of our f of x? Okay. I probably could have gone ahead and put in that value. So what is the limit as x approaches 2? Okay. Well, graphically, since I have sketched the little graph here, we don't always have to sketch the graph. And if I hadn't sketched it, I would do this analytically. But since we do have the graph here, let's think about this. Well, we need to think about what is the limit as x approaches 2 from the left, and what is the limit as x approaches 2 from the right. Okay, from the left, as x approaches 2 from the left, the y value, the intended y value, what's y going to? Well, y is going to negative infinity, right? So this limit from the left is negative infinity. What about from the right? Well, from the right, as x approaches 2 from the right, the y value is going up. It's increasing without bound. So this y value is going to infinity. It'll never reach it. It's just going there. Okay? Now, before I go too much further, know this. If you get infinity or negative infinity for a limit, I want you to write that, and then I want you to write does not exist. A limit has to be a number. Okay, so if an infinity is not a number, infinity is a concept. It represents an unbounded value. So when you get infinity or negative infinity, that does not exist. This does not exist. Okay, but knowing that it is infinity or negative infinity, that tells you something. Okay. If we had not drawn the graph and seen that vertical asymptote, when I get a limit, a one-sided limit that is negative infinity or infinity, I know I'm dealing with a vertical asymptote. I know when I get this, I'm dealing with a vertical asymptote. Okay? So even if I just got one of these, I'm still dealing with a vertical asymptote. Now this limit, the limit as x approaches 2, that does not exist. For two reasons. For one reason, neither of the one-sided limits exist. Okay? And they're certainly not equal. All right? So lots to keep in mind with that. Lots to keep in mind. So let's kind of summarize. Let's kind of summarize what we have here. Let's see what I wrote down. Things to keep in mind. Things to keep in mind when looking at a graph to evaluate a limit. Okay. All right. First of all, every one-sided limit exists unless that limit is infinity. So the only time that a one-sided limit does not exist is if it's infinity. You'll never say that a one-sided limit is 3 and therefore it does not exist. That doesn't make any sense. So every one-sided limit from the left or to the right, that exists. It is a number unless it's infinity. Okay? Number 2, for a regular, not one-sided limit, if there's a hole in the graph, then the limit exists and is the y value of that hole. if there is a break in the graph, not a hole, just a break, a complete break in the graph, then the limit does not exist. Does not exist. DNE. Okay. The limit as x approaches infinity or negative infinity gives you a horizontal asymptote if it exists. All right? If it exists. It doesn't have to exist, but if you have a horizontal asymptote, that's the limit as x approaches infinity or negative infinity. And then lastly, if you get a limit of infinity, so if your answer to a limit, a one-sided limit, is infinity, then you have a vertical asymptote. Okay? Keep in mind that this would be a one-sided limit. Okay? And limits of infinity do not, it's still a DNE. It still does not exist. Okay? All right. On to, okay, so now what if we don't have the graph? Because we're not always going to have a graph. Okay? We won't always have a graph. So what about if we don't have a graph and we don't want a graph, can we still find a limit analytically? So in this next little subsection, we are going to be finding limits analytically. Okay? So we have a few different methods for doing that, and they always start at the same place. They always start with substitution. Always. Okay? Technique 1, substitution. Okay? Let's take a look at an example. Let's say we have the limit as x approaches 1 of this rational function. Okay? You should always begin by just simply substituting in that x value. See if you get a number. If you get a number, you're done. Okay? Now, here's the only thing I want you to consider. When you put this 1 in for all of the x's here, think of it as this is going somewhere. It may not equal it, it's going there. Okay? So when I put it up on top, when I put 1 in for x here, this numerator is going to what number? Well, this numerator is going to -4. Okay? Because a limit, x is going to 1, so the numerator is not actually equal to -4, it's just super close to -4, right? Remember that as x approaches 1, we're only approaching it. We're not actually equaling 1. Okay? The denominator is going to what? Well, the denominator is going to -2. So this entire fraction is going to 2, right? -4 over -2. This is going to 2. I'm done. If I get a number, I'm done. Okay, let's look at another. Well, let's come over here, B. Let's say the limit as x approaches -4 of 4 plus x over 3x plus 10. All right. So in the numerator, what is the numerator going to? Well, the numerator is going to 0. The denominator is going to -2. Can you divide 0 by -2? Yes, you can. 0 divided by -2 is just 0. Is 0 a number? Yes, it is. So this is just equal to 0. And we're done. Okay. Let's take a look at this one. Let's let x go to 3 of 2x plus 5 over x minus 3. Okay. The numerator is going to 11. 2 times 3 plus 5. The denominator is going to 0. So we have 11 divided by 0. Can you divide 11 by 0? The answer is no. You cannot divide 11 by 0. Okay? You cannot. 11 divided by 0, keep in mind what happened when our denominator is 0. Let's take a look at it. Let me take a look at it this way. The limit as x approaches 3 from the left and the limit as x approaches 3 from the right. Okay? The numerator in both cases is just going to 11. Both cases going to 11. Okay? So 3 from the left, I'm thinking of 2.99999999999. If I put that in for x, this is, yes, it's going to 0, but is it positive or negative? Well, it's going to be negative because we're going to have a very, very tiny negative number. Whereas on this one, where we're approaching 3 from the right, that's like 3.00000000001, right? Yes, this is going to 0, but it's positive. Okay? When you divide 0 by a a number that's very close to 0 but negative, this is going to negative infinity, which is a DNE. We've got a vertical asymptote. Whoops, asymptote. There we go. Here, 11 divided by a number close to 0 but positive. This would be positive infinity, DNE, another sign of a vertical asymptote. So our limit that we were trying to evaluate up here does not exist because we have a vertical asymptote. A limit does not exist on a vertical asymptote. Okay? So 0 on top, that's fine. 0 on the bottom does not exist. Okay? All right. What if we had this? The limit as x approaches infinity, of 7, let's just say 7 over x. 7 over x. If you think of plugging in an unbounded number, the biggest number that you can possibly think of, put that in for x. What would 7 divided by that biggest number that you can think of be? 0, right? That's just 0. Okay, this means we have a horizontal asymptote at y equals 0. Okay. Similarly, what if we had this? What if we had x squared over 7? Now plug in your unbounded number for x. What would your unbounded number, the hugest thing you could ever think of, divided by 7? What is that? Actually, you got to square it first and then divide it by 7. It's still infinity, right? That's still infinity. Does not exist. Okay, so here the top was 7, the bottom was going to infinity. 7 over infinity, 0. Here the numerator was infinity. Infinity over 7, still infinity. It makes sense, right? Okay. Now, what if we get like 0 over 0? or infinity over infinity? What if I put some other x's down here and we had other things going on? If you get 0 over 0 or infinity over infinity, then you cannot do the substitution method. You have to do a different method. So if you have 0 over 0, infinity over infinity, or negative infinity over infinity, these are three types of what is called an indeterminate form. There are others, but these are the three types that we see here in this first unit. We will meet others later on. I believe it's in January we get there. Maybe later. No, I think it's in January. Anyway. All right. So if when you use substitution, if you get one of these indeterminate forms, then you don't know the answer immediately, and we have to use a different technique. And the first of these different techniques is the factor and reduce method. Factor and reduce. And I'm going to put after this, then substitution. Then always remember to go plug in your value for x at the end, all right? So first factor and reduce. So let's take a look at an example here. Let's say the limit as x approaches 2 of 2x squared minus x minus 6, all divided by the quantity 2x minus 4. Well, if we just put in 2 for x, we're going to have 2 times 4, so 8, minus 2 is 6, minus 6 is 0, right? So the numerator is going to 0. What is the denominator going to? Well, it is also going to 0. We can't handle that, so we have to do something else. So in this case, I notice that we can factor the numerator and we can take out a 2 on the denominator. So that's what I'm going to do. Now, it is very important you do what I'm about to do. Put an equal to sign. Okay? Then rewrite the limit as x approaches 2. We have to rewrite that. Do not just say that this is equal to and then start factoring. You need to rewrite that limit. Otherwise, you're saying that this limit is equal to that fraction and that you're writing something that's not true. Notation, communicating how you do your work in calculus is crucial. Okay? All right. So now let's go ahead and factor. Let's see, we have 2x and x. I need a 3 and a 2 probably, so I think I need to put the 3 here and the 2 here, and the 2 needs to be a negative to get that negative x. There we go, so that'll work. I got my 2x squared minus 4x plus 3x will give me that minus x, and then minus 6. All divided by, take out just a 2, and here we see, now I see the reason that I got the 0 over 0. The reason we got 0 over 0 was because there's a hole in the graph of this function. There's a hole right at x is equal to 2. Okay? So now I see what was happening. So yes, you can cancel this out because we don't care what happens when x equals 2. We only care what happens when x is approaching 2, right? So yes, we can cancel this out. And then we plug in 2 to what remains. So now I'm plugging in 2 for that x right there. And now this is going to 7, right? And this is just 2. So we have 7 over 2, and we're done. When you can plug in the 2 and you get a number, you're done. Then you do not have, now you stop writing your limit because you have said what the limit is equal to. Okay? All right, let's do another. let's say we have the limit as x approaches -3. And I'd like to review with you real quickly factoring a perfect cube, or a sum of cubes. This works for a difference of cubes as well. Alright, but first of all, if you just plug in -3 for x, if you just substitute in -3 for x, we'd have -27 plus 27, so the top is going to 0. The bottom is definitely going to 0 as well. 0 over 0 tells me we have more work to do. So we are going to factor here. Okay, how do you factor a sum of cubes? Well, a sum of cubes factors into a binomial times a trinomial. A binomial times a trinomial. To get the binomial, you just take the cube root of both of these terms and you keep your sign. So the cube root of x cubed is x, the cube root of 27 is 3, and we keep the plus. To get the trinomial, you start with your first term in this parentheses, and we square it. So that will be x squared. The last term will be the 3 squared, 9. The middle term will be the product of these two, not twice the product, just the product, 3x. Okay? When we squared the 3, that's positive, so this is always going to be a plus at the end. This sign, however, we have to take the opposite of this sign, so it'll always be the opposite. If this had been a minus, then this would be a plus. If this is a plus, then this is a minus. If you're unsure, gosh, I wonder if that's right, you know what you could do? We could go ahead and FOIL this whole thing out, distribute it all out, and we would get exactly this again. Lots would cancel out, and you'd be getting that again. You might see now why you have to have a minus, because if this was a plus, if it was all pluses, then we would have an x cubed term, an x squared term, an x term, and a constant. And we don't have the x squared term and the x term, so that we have to have a minus involved somehow to get rid of those. All of this is divided by x plus 3, which we cannot factor. Okay, now again, I see what was happening. I see an x plus 3 on top, x plus 3 on the bottom, so now I realize, oh, well, no wonder I had a 0 over 0. I have a hole in the graph. So that's what was going on. So I had a hole in the graph. I can cancel that out. I can cancel those two terms out because I don't care what's happening right at x equals -3, only approaching -3. And now I plug -3 in for my remaining x's. This is going to 9. This is going to 9. This is going to 9. So this whole thing here is going to 27. The bottom, we have a 1 on the bottom, right? So this limit is 27. Okay? So that would be our second thing that we would try to do if we got one of these indeterminate forms. Well, this would be our second technique, and it's probably the first one I would do if I got an indeterminate form like this. Okay. But we have other things. What if we can't? What if we cannot factor? Because we cannot factor lots of things. What if we had? Let me give you this. Let me give you the example first, and see if you can think of something that we could possibly do. On this one, before I just. I think I just cut out on you. Sorry about that. Let's see something. Okay. Anyway, alrighty. What if we have this? So if I just try to substitute first, my numerator, the square root of 16 is 4. 4 minus 4 is 0. So I have a 0. the numerator is going to 0. The denominator is also going to 0. That's one of my indeterminate forms, 0 over 0. So I cannot just substitute. What else can I do? Well, I can't not factor this either. So what else can we do if we have something like this? And when I see a little square root or more than one square root up here, I think, oh, let's try to multiply top and bottom by a conjugate. So this technique is multiply by a conjugate. Okay. All right. So I'm going to multiply top and bottom by the same thing here. I'm going to multiply, I see the square root of, I go to where my square root is, so square root of x minus 4. The conjugate of square root of x minus 4 is square root of x plus 4. Okay, so I'd like to multiply by that. But I cannot just come in and multiply by that. Whatever I do on top, I have to do on the bottom. This way, I'm multiplying by 1. This is just 1, right? It reduces to 1. So I'm multiplying this by 1, which does not change the value of it. We do not want to change the value of this function. Multiplying by 1 will not change the value. Okay, so I'm going to come in here. Let's multiply this out. Okay, I'm going to go ahead and put parentheses around top and bottom. So on top, I'm going to FOIL this out. So square root of x times square root of x is x. 4 square root of x minus 4 square root of x is 0. That's why we multiply by a conjugate. It gets rid of that middle term. Okay? And then we have, for the last term, minus 16. So x minus 16. Now on the bottom, I definitely do not want to multiply this out. Because if I multiply this out, I'm going to lose my chance to cancel something. I want to leave this x minus 16 where it is. Because look what's on top. Look what I can cancel out in a second. So do not actually multiply out the denominator or the whichever, the top or the bottom, whichever one you were not taking the conjugate of. Now the x minus 16 on top. Now we have a whole, right? And the x minus 16 on top cancels with the x minus 16 on the bottom. We are leaving a 1 on top. And now we can substitute in 16 for the remaining x. So this denominator is going to 8, so this limit is equal to 1 over 8. Okay, what about this one? B. Limit as x approaches 0 of sine x over cosine x minus 1. You will get very, very used to, in this course, you're going to get very used to having trig functions, log functions, exponential functions, rational functions, all of the function types that you have been introduced to in the past. They will be in everything we do. Okay? So seeing a trig function eventually will not surprise you at all. Okay? Let's begin by letting x go to 0. So we're going to substitute. Sine of 0, you need to know all of these values. Sine of 0 is 0. So this numerator is going to 0. Cosine of 0 is 1. So this denominator is also going to 0, because 1 minus 1 is 0. Okay? So when you look at this, function, it may not be obvious to multiply by a conjugate, right? It will be obvious after you practice these. Then it will be more obvious. But at first it's not obvious why you would multiply by a conjugate here. Practice, 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 and then it will be. Okay? But we certainly cannot factor this. So I am going to multiply top and bottom by a conjugate. And the only thing I can take a conjugate of is this cosine x minus 1. So I'm going to multiply top and bottom by cosine x plus 1. Okay? Parentheses, parentheses, parentheses. Okay. All right, so this is equal to limit x approaches 0 of, all right, on the top, I'm not going to multiply, right? Because if you do, you're going to lose something to reduce. So just leave it. Sine x times cosine x plus 1. In the denominator, that's where our conjugates were, so that's where we want to multiply. So we're going to have cosine squared x. The middle term zeroes out, minus 1. Now in the denominator, we need to recognize that. We need to recognize what this is. We had our main Pythagorean identity in trig. Our main Pythagorean identity said that sine squared x plus cosine squared x is equal to 1. Do you remember that? Well, we have cosine squared minus 1. Can I manipulate this to get cosine squared x minus 1? Yes, I can subtract the 1 over here and subtract the sine squared to the right. Then I would have cosine squared x minus 1 is equal to a negative sine squared x. So I can replace cosine squared x minus 1 with negative sine squared x. And that's exactly what I'm going to do. And now I can reduce. Sine x on top, sine squared x on the bottom. This sine x reduces with one of these two sine x's, leaving cosine x plus 1 divided by a negative sine x. And now I'm going to put 0 in for the remaining x's. Cosine of 0 is 1. 1 plus 1 is 2. So this numerator now is going to 2. Okay? The denominator, sine of 0 is 0, right? So the denominator is going to 0. Can we divide 2 by 0? No, we cannot. We are dealing here with some kind of vertical asymptote. So this is, I shouldn't say, it doesn't equal DNE, it just does not exist. Does not exist. Okay? All right, so we've done substitution, factoring, multiplying by a conjugate. There is one more thing that you might see in one of these problems, and like I did the last time, what if we have this limit, before I tell you the name of the technique, what if I had the limit as x approaches negative 5 of 5 over x plus 1 in the numerator, and in the denominator 5 plus x. What if we had that little guy? Well, if I plug in negative 5 for x, I get negative 1 plus 1 on top. So that the numerator is going to 0. The denominator is also going to 0. That's indeterminate, so we need to do something with this. I can't factor. I cannot do a conjugate. No conjugate would work here. So all I can do here is kind of simplify this complex fraction. Okay? It is a complex fraction because it's a fraction within a fraction. So this technique I'm calling simplify a complex fraction. Okay? So to simplify this complex fraction, the thing that's making it complex is this little guy right here, right? So that's what I'm going to multiply top and bottom by. Again, I'm multiplying by 1. So I'm multiplying top and bottom by that little x. when I do that, I have 5 over x times x, that leaves me just the 5, plus 1 times x, that's x, over, and down on the bottom, don't multiply, just leave it. 5 plus x times x. You don't want to multiply because look at what you have on top. Those are going to reduce. Now I see what was going on. I have a hole in the graph. So this reduces with that 5 plus x. We're left with a 1 on top. And now let x go to negative 5. So x is going to negative 5. So this limit is just negative 1/5. Okay. One last little example here. Limit as x approaches 3 of, okay, 5 over x plus 2 minus 4 over x plus 1, all divided by x minus 3. Okay, always try just to substitute first because you never know. If I substitute 3 in for x, I get 5 over 5, which is 1, minus 4 over 4, which is also 1, so 1 minus 1 is 0 on top. If I put 3 in here, I get 0 on the bottom. So I have 0 over 0, that's indeterminate. So next thing I see is this complex fraction. I know what to do. I'm going to multiply top and bottom by whatever is in the small denominators. So the x plus 2 times the x plus 1 in this case, over itself. Okay? All right. The 5 over x plus 2 times x plus 2 times x plus 1, the x plus 2's will cancel. I'm left with the 5 times x plus 1. And if you wanted to, you could go ahead and distribute that out there, but I think I'm going to wait. Minus 4 times, now the x plus 1's will cancel, and we're left with the x plus 2. All divided by, and down here I am not going to multiply anything out. I'm just going to leave it with these 3 factors. Okay? All right. Now I am going to go ahead and simplify this numerator. So I'm going to distribute and then combine my like terms. So up here I have 5x plus 5 minus 4x minus 8, all divided by, and on the bottom I'm leaving it alone. I'm leaving it alone because I know something is going to reduce out. I just don't know what yet. Well, I do know what. I know it's going to be this x minus 3. I know that's the whole thing. That's what I want to get rid of, right? That's the whole thing that's causing me the problem is the x minus 3. So I do know what's going to cancel out. That's the thing that always cancels out in these problems. Okay, so here we have an x minus 3 on top. Not shockingly, it will reduce out. So now I see what was happening. We got a hole in the graph. No wonder we got 0 over 0. So this reduces with this, leaving me a 1 on top. And I substitute the 3 back in the bottom, and I get 1 divided by, and on the bottom, this little piece is going to 5. This little piece is going to 4. So the whole denominator is going to 20. Right? And that's it. So we've done quite a bit here. This has been a little bit longer than I expected it to be, but that's okay. It's a nice review. So this was a review of limits for some of you, but it was your entire exposure to limits for some other of you, and that's okay. This was a pretty thorough look at limits. Okay, I think you'll be in good shape for what we're doing in this first unit with limits, but it will take practice on your part. So I have very generously provided you with lots and lots of practice problems, okay, and the solutions for those. So now it's your turn to go and get a head start, and to go and practice on your own. Bring me whatever questions that you have, okay? Before I leave you, I want to mention something. I want to mention with you that this whole idea of a limit being the intended height or y value, know that that is a very casual definition. That is not a rigorous mathematical definition at all. There is a much, much more rigorous definition of a limit. We just don't need that in this course. We don't need it in this course. But if you are interested in it, you can look up the epsilon delta definition of a limit. And that is the formal, rigorous definition. Okay? Some of you might be interested in that. All right. That's it. Now you guys go practice.